Okay, so what I want to do today is, this is the last class before Thanksgiving break. I want to do some fun applications of probability. I want to show you how the stuff we've been doing can be used. Before we do that, I do want to talk about probability in the news. Anybody watch Sunday Night Football? What happened at the very end of the Bengals-Cardinals game?
Yeah, it was a penalty for calling the count from the defensive side.
An extremely obscure penalty, but if you're on defense, you are not allowed to pretend to be on offense and say what the offense is saying to try to confuse the offense as to when the ball is going to be snapped. And so it was a 15-yard penalty, reduced a little bit because the Cardinals were so close to the end zone. But there's some really nice articles about how does this change the win percentage of the team by being moved forward versus if the refs had not heard and the offense does a false start, they lose 5 yards and a mandatory 10-second time runoff, and they may not actually have enough time to get the kickoff. So it's a really good analysis of what is your optimal choice in a situation like this when you're facing a good kicker. Right. What I want to do now is I want to shift gears and talk about the central limit theorem. So I want to talk about Monte Carlo method. This is one of the most important ideas in mathematics. There are many people who say that this was the greatest achievement of mathematics in the 20th century. It allows you to simulate very complex phenomena well. It basically is built on the central limit theorem. One of the earlier instances of its use was actually in trying to understand the process to build an atomic bomb and dealing with extremely complicated interactions. What is the big lie from Calc 2? You can integrate. Okay, that is the big lie. You cannot integrate. For those of you who feel you can integrate, I'm happy to take you down. Okay, you can't. We work really hard to give you this false sense of achievement. Okay, you're adults, you're old enough, some of you are going to go into this thing called the real world, and it's time you understand what's going to happen. You will have functions that you cannot integrate. Well, this doesn't seem too bad. I mean, integration is just something to do to keep you busy in college, right? Nobody actually cares about finding integrals, right? Why do we care about finding integrals? Probability. This is a probability class. You know, when in doubt, motivation is probabilities of events. That's why integration is so important, is we want to calculate what's the likelihood of something happening. And you need to find areas under curves or areas between curves or areas of regions. And so I will not venture my personal opinions about things, but in economics, a lot of the integrations you need to do are unfortunately too difficult to be done in closed form. And what you have to do is, if you want to see what happens as you change the parameters, you have to just do lots and lots of simulations, or you have very nasty regions to integrate over. And one of the things you can do is you can simulate. So we started off with a picture on a dartboard. There's actually some picture behind it. Let's imagine that that's a unit square. How do you think we could estimate the area of the picture? Yes?
Is the picture the unit square, or there's a picture behind?
There is a picture behind the unit square. So I will try to walk over right now and show. Can you turn on the lights? Thanks. So in honor of tonight, here is the picture. So how could we estimate what the area of this picture is? Yes?
Number of darts that hit the picture over the number of darts that hit the unit square.
Excellent. What's the area of the unit square?
1.
1. That makes the calculation particularly nice. Could we have used a rectangle that was 2 by 5? Absolutely. And so all we need to do here is see what fraction of the dots hit the unit square. Well, hopefully that's all of them, but if not, what do we do to the dots that don't hit the unit square? We ignore them, right? This sounds very similar to our conditional probability. You know, we just care about the events that are hitting the unit square, and then we see what fraction of the time do we actually hit our image. What do you want to assume about your dot throwing? It's random. Okay, we need more than just random. Independent and probably uniformly distributed in the square. Do you think your dot throwing is random? I'd be willing to grant random, but I would not be willing to grant uniform. What do you think most people are trying to do when they throw dots? Yeah, probably trying to get towards the center. Based on how many are near the center, we have some assessment of skill in this class. Why are you trying to get in the center?
Minimizes your chance of missing.
Yeah, minimizes your chance of missing. I was talking about there would be some penalties if you hit the board. Nobody, of course, hit the board in this class. We caused no damage in this demonstration. But when you're trying to hit the piece of paper, you will be tempted to try to throw it towards the middle to maximize your chance. We need ways to simulate uniform random variables. Fortunately, there are ways to do that. There may be better ways to do that. And what we want to do is we want to figure out what fraction of the time we hit the region. So we just count. And then we divide the fraction that hits by the number of times we do it. Now, what theorem do you think is going to come into play to help us estimate the area? What do you think will come into play? Central limit theorem. So as you take more and more shots, what fraction of the time do you think you should hit? Yeah, basically the area, because it's a unit square. If it was something of area 5, I would say the area of my region divided by 5. And then the question is, what's the scale of my fluctuations? And we'll go through this in a moment. So what I've done is I've written simulations to try to calculate the area of 2 different regions. I'm trying to do it like this so that the people watching at home who had to travel a little bit early. Okay, so Mathematica allows you to make, using the manipulate function, nice movies. So as soon as anybody can figure out what the region is, let me know. Red means you're inside the region, blue means you're outside. Any guesses? All right. What do you think? Unit circle. And so what we can do is we can speed it up a little bit. Speed up a little bit more. Oh, I'm slowing it down. Sorry, let's go the other way. And you can start to see it filling in. And it's keeping a running tab over here of the area. I'm not doing a unit square. I'm doing a square that's 2 by 2. That makes a lot more sense when we're doing a unit circle. And what you can see is it keeps track of the number of data points. And it gives you this number here. So according to theory, what should that number be? Pi. And I just realized I'm probably holding this upside down. But it doesn't really matter because all I'm doing is showing a picture of, so the GoPats logo is probably upside down, but the nice thing about the symmetry here is it doesn't really make too much of a difference. Okay. And so right now we're at around 6,000 points. I'll stop when it gets to around 7,000. Okay. So 7,000 points and we get 3.16. Are you impressed or not impressed? It's not horrible. It's almost 2 digits accuracy. If we go all the way to the end, let's see, does it let me go all the way to the end? All right, so if we go to 7,620, we could probably go a little bit farther. It's 3.158. Much better than the Indiana State Legislature many years ago. They wanted to do, I think, 3.2. When you look at the picture, does it look like the dots are uniformly distributed? Why not? There's clumps. How many of you have randomly thrown 7,000 plus dots at a unit square in your life? Okay, wait, did somebody raise their hand? Okay. If I had said 4,000, no. So be very careful in extrapolating from real world experience. Did I tell you the quote from my physics book from high school on relativity? It said that at first when you look at these results from Einstein's theory of special relativity, they seem surprising, but you have to remember most people don't have experience traveling at 3/4 the speed of light. I always found most a little bit amusing. I've yet to find anybody who has experience traveling at 3/4 the speed of light. But the point is a really good one. You've got to be extremely careful about taking a lesson in one place and extracting something that you then assert holds in someplace else. Another great quote by Mark Twain. If you need good quotes, he's a great person to turn to. A cat that jumps on a lit stove. How many of you have heard this one? Excellent. What's the quote? For cultural extra credit. Okay, a cat that jumps on a lit stove will not jump on a lit stove again, nor will he jump on a cold one. From each lesson in life, only extract the lesson you should. This is, again, paraphrasing. Mark Twain said it much better. But it's easy when you see something to push it to places where it shouldn't. I gave you some links for what happened in Wall Street when they were using certain formulas in places where they had no right to use them. You've got to be very careful. When you say that this is clumping, well, should they be clumping? How much clumping should there be? So there's a beautiful theory about how uniformly distributed points should look. Well, if it's uniformly distributed, that's some kind of lattice structure. That's pretty straightforward. These are not uniformly distributed points. These are points chosen uniformly at random. And then when you do something like that, what kind of pattern emerges? Think back to coin tossing. For runs of heads and tails, for consecutive heads, how many consecutive heads do you expect? We do expect stuff like this to happen. We do expect there to be accumulation. So the question then becomes, is there too much here? Are there too many areas of white? It turns out there are actually better ways to do. I hope that doesn't mean the pats are going to fall tonight. It turns out that there are better ways to do things than just choosing points uniformly at random. You can do some kind of quasi-random pattern involving the Fibonacci numbers and the golden mean. And what's nice about something like that is if you know exactly how many data points you can take, that will affect, oh, I can't wave my hand because that will adjust this. That will affect how you choose your points. But what if the simulation runs a little bit faster than you expected and you have a little bit more free time so that you can run a little bit longer? Well, if you have a lattice pattern, if you start adding in a few extra points, you're not going to be able to add them as you would like. But there is a way using Fibonacci numbers and the golden mean to actually have something where as you get more data points, you put it in exactly as you would like. All right, let's do one more region. Can anybody recognize what this is? Any thoughts? All right. Any thoughts yet? Ellipse. All right, so around 1,000 data points, you got it as an ellipse in honor of Monday Night Football. And it says the area is about 1.66537. And this is an ellipse that has major axis of length 2, minor axis of length 1. Or semi-major axis of length 1, semi-minor axis of length 1/2. Most of you probably do not remember the formulas for areas of ellipses. Does this seem reasonable? Does this look like any famous number? It looks a lot like pi over 2. So if we keep running, and we'll crank up the speed. How do I stop? All right. So here's 7,570 points. And again, we still see lots of clumping. We see regions over here where there's no points. We see regions where there, oops, let's try to get down here, where there seems to be a lot of points. And we're getting about 1.59. If you double 1.59, what do you get? I'm sorry? Yeah, around 3.2. A little bit less, but not much less, because it's 1.598. So the pi over 2 conjecture seems very reasonable. And this is a great way to use data to build up some intuition. So what I thought I would do for the rest of today is talk a little bit about how to use Monte Carlo integration, how to use the central limit theorem to calculate these values. Oh, okay, good. I did not quite swear. It just has the counting number upside down. All right. All right. So interesting. So today it's actually swiveling beautifully. All right. Monte Carlo and the central limit theorem. All right. So the setup. We have a nice box. And we have a nice region in the box. And we're going to assume it's easy to tell if we're in the region or not in the region. So for instance, maybe I have some very painful functions here's my f top of x, here's my f bottom of x. And for each point, I can just check and see, is it greater than f bottom and is it less than f top? And if so, I'm inside the region. These may not be integrable functions, or they may not be functions that have nice closed form integrals. That's okay. All that really matters is I have a way to determine if I'm in the region or not. Okay? And now what I do is I keep throwing dots, and I see what fraction of the time I land inside. So throw n dots. Okay, well we're not going to really throw dots unless we want to do finance. We're going to choose n points IID RV uniform. Okay, well now that we're doing this, we can try to figure out what fraction of the time we should land inside. So what fraction do we expect inside? Well, let's let xn be 1 if inside and 0 if outside. What's the probability we land inside?
Fraction of the area.
Area of A. And this happens with probability area of A. And this happens with probability 1 minus area of A. So let's just call this P sub A and 1 minus P sub A, just for convenience. Yes?
Are we assuming the box is the unit square?
So we'll assume the box is the unit square. So assume box is the unit square. You know, it makes absolutely no difference in terms of the general theory. It just makes the notation a little bit simpler. So now, same thing as before. Let's let y sub n be x1 plus x2 plus xn. So what I love about this problem is we get to review so much of what we've done all semester and see in application. Can anybody tell me anything about yn? Yes?
As n gets bigger, it's going to look like the standard or a normal.
It's going to look like A normal. Is this really the quantity we want to study? Do we really want it? No, what would we want to study? It's going to be very close to this.
The fraction.
Yeah, we should probably divide this by n. And you see, what fraction of the time do we land inside? What's the expected value of yn? P of A. So again, whenever you see a probability distribution, your first question should be, what's your expected value? Your second question, what's your variance or your standard deviation? You have a little bit of freedom, but not much. What's the variance of yn? So what's the variance of each one of these? PA times 1 minus PA, because it's a binomial. We have n of them, but we have a fraction of 1 over n from each one of them. So you square the 1 over n. So you have n over n squared PA 1 minus PA. Well, n over n squared is the same as just 1 over n. Or I can probably write this more concisely as just PA 1 minus PA over n. And you can begin to see now why this is such a powerful method. As n gets very, very large, what's the expected value of y converge to? It converges to the correct answer. It's always nice if you're doing some kind of simulation that it converges to the right answer. The next thing is you would like to know that it's converging tightly. It would be horrible if half the time you're, say, off by 2 below and half the time you're off by 2 above. On average, you're fine, but you're never getting a good read. Well, what this is telling us is that as n gets very, very large, it's getting very, very tight. What could we use to quantify how tight we are? I'm sorry? We could, right, but I mean, I need a theorem. Chebyshev. We could start off with Chebyshev. And Chebyshev is already going to be enough to give us some kind of good convergence. And we saw this for like the weak law of large numbers. But we are not doing a generic distribution. We're doing basically coin tossing. We're doing a nice binomial. We can do something much better than Chebyshev. What could we use? I'm sorry? Yeah, probably the big thing written over there, Monte Carlo and the central limit theorem. Central limit theorem. What's the biggest difference between Chebyshev and the central limit theorem? Chebyshev, think of it as, well, you can use it if you have multiple random variables. You think of it as, I'm using Chebyshev because I have a random variable, I have its mean, I have its variance. The central limit theorem is you have some kind of process that's happening many, many times. So because I have a process that's happening many times, I expect to get really good results. I expect some kind of normality to come into play. And what the central limit theorem will tell us is that yn is going to converge to becoming normal with mean p of a and variance pa 1 minus pa over n. So this is going to be, I'll do approximately if n is large. It'll be approximately normally distributed with mean pa and variance pa 1 minus pa over n. So you can now start to quantify what's the probability you differ from the true answer by 1%. It's going to be extremely small as n gets large. Your fluctuations, let's think about the scale of fluctuations. You always want to study the scale at which things happen. This is of size p of a. P of a is a number between 0 and 1. What's the size of the variance? On order what? So what's the size of the variance? I need to know roughly how big is the variance. This is on the order of 1, the probability. What's the order of the variance? How big is this approximately? Yes?
1 over n.
It's about 1 over n. Yeah, there's some constant over here, and this constant's related to the true area. But roughly the variance is of size 1 over n. What's the size of the standard deviation? This is going to be, the square root of pa 1 minus pa over square root of n. We expect the standard deviation to be on the order of 1 over square root of n. So when I look at my fluctuations about the true value, I expect my fluctuations to be a couple multiples of the standard deviation. If I went log n fluctuations away, even Chebyshev is enough to say that that's improbable. The central limit theorem would say it's damn improbable. So you can basically say we expect to get pa times n. That's how many hits we expect to have, plus or minus, say, some constant times 1 over square root of n times n divided by n. So if you wanted to just look at what your hit count is, you expect pa times n hits, and your fluctuations you expect to be on the order of 1 over square root of n times the number of tosses. So when we do this, we get basically pa plus something of the size constant over square root of n. So this gives you an idea of roughly how accurate you are as a function of tosses. You expect to be accurate to about 1 over square root of n. You can even quantify this by using the central limit theorem to say you have a certain probability of being within 2 standard deviations. We're here? Oh, yeah, it should be plus or minus. So you could use the central limit theorem to say, what's the probability we're within 2 standard deviations, within 4 standard deviations? What's the worst case for us for PA in terms of our error? Worst case for our error? I'm sorry? PA is 0.5. So PA times 1 minus PA is maximized at a half. Does that make sense that our variance is worse at a half? Yeah, that's when you have absolutely no information. You're equally likely to be in or not to be in. Imagine the extreme case when PA is 1. You can't help but hit it. This is the throwing the person out of the boat into the water. You have to hit it. What's your variance going to be? 0. Conversely, if your region has area 0, you always miss. And so you expect when PA is close to 0 or 1, the variance is going to be very small, or at least have a very small constant here. And you expect as PA gets closer and closer to a half, it's going to be much harder. And the fluctuations are going to matter more and more. So when you look at this, you have some reasonable claims. We expect, who's done statistics? So if I want to be 95% sure, how many standard deviations? 1.96. So if you're within 1.96 standard deviations of the mean of a normal distribution, that corresponds to 95% of the mass. Anybody remember to be 99%? What is it? That's not 1. I think it's 2.54 or 2.56. It's either 2.54 or 2.56. Something like that. So about 2.5 standard deviations gives you 99% of the mass of the normal. If you go up to 4 standard deviations, it's ridiculous how much of the mass you have. We threw about 8,000 data points. We did n equals 8,000, which is roughly, well, that's okay. We'll do it at 8,000. Anybody tell me roughly what the square root of 8,000 is? Approximately? Square root of 8,000 is roughly what? I'm sorry? 90. This is approximately 8,100. The square root of 81 is 9. The square root of 100 is 10. This is approximately 90. So 1 over the square root of n, and this is why you always do circles, is approximately 1 over 90, which is approximately 0.01, ballpark. How accurate were we when we were simulating the area of a circle or an ellipse? We were basically missing in the hundreds digit. That's exactly what you would expect from this analysis. You would expect that we should be within about 1 over 100. And then this will be a little bit larger because we have the constants here, maybe a little bit smaller. Well, it's a little bit smaller because this is less than 1, but then we're multiplying by a few standard deviations. Ballpark, we were where we should be. Well, I'm not surprised. We're doing the central limit theorem with 8,000 observations. If you've taken statistics, how many of you have taken a statistics course? There are a couple of things, it's almost biblical, where Moses comes down from Mount Sinai and he has these commandments that thou shalt use in statistics. How many observations do you need for the central limit theorem to kick in typically? I'm sorry? Yeah, typically 30. Statisticians say once you have 30 data points, it's normal. We're at the order of 8,000. And we're doing a really nice distribution. We're just doing coin tosses. So we should be extremely confident at this point. Okay, any questions on this? So to me, this is one of my favorite applications of probability, is just seeing how this can be used for something that really matters. How can we approximate integration really well? There's some extremely good higher mathematics in how do you randomly simulate points, and how do you simulate points with some kind of quasi-random structure. And I'll put up some reading on stuff like that. Before I do Buffon's Needle, it seems natural to turn today into an integration day. And so how many of you know how to calculate the area of an ellipse? I'm trying to see who's had calculus with me before, because I know I've done this in my calculus class. All right, so what I want to do is I want to quickly do how you would calculate the area of an ellipse or the volume of an ellipsoid. These are all the same calculations. It allows me to review one of my favorite methods, integrating without integrating. We convert the problem to something we know. So do people want to do the area of an ellipse or the volume of an ellipsoid? Area. All right. Area of ellipse. So an ellipse is of the form x over a squared plus y over b squared is less than or equal to 1. This is an ellipse that is adjusted to live along the xy axis. For those of you who have seen linear algebra, you can actually write this as xy 1 over a squared, 0, 0, 1 over b squared, xy less than or equal to 1. And there's a whole theory of matrices related to ellipses and conic sections. And what's nice about this is if I give you an ellipse like this, in high school you get very upset, because now it's not aligned. If you were to take linear algebra, what would you do if I gave you an ellipse like this? Yeah, change bases. You basically just lean back like this and say, I'm going to work in this basis, u, v. And in this basis, you can now write it down very nicely. And you get between these two bases by an orthogonal change of variable. And so you write it down in uv, and then you rotate back, and you get an xy. So really, all these conic sections come down to nice linear algebra results. All right, let's go back over here. If you could choose a value for a and b, what value would you choose for them? 1. Or more generally, you could have them both be r. So if a equals b equals r, it's a circle of radius r. We understand the area of a circle of radius r. So we're going to change variables. Let's let u equal x over a. Let's let v be y over b. du is 1 over a dx. dv is 1 over b dy. So combining these together, we get dx dy is ab du dv. And so we'll see if I set things up the right way. So if I integrate over the region x over a squared plus y over b squared less than or equal to 1 of 1 dx dy, what does this region become in uv space?
Just u squared plus e squared
U squared plus v squared
less than 1.
less than or equal to 1. And then the whole point is I need to figure out my change of rows. How does dx dy transform into du dv space? It's just ab du dv. This is a nice integral. What's this integral equal to? Pi ab. And there is the formula for the area of an ellipse. In the special case when a equals b equals r, it reduces to a circle, which is good. You always want to check and see, does your formula make sense in extreme cases? If you had 3 components, if you had x over a squared plus y over b squared plus z over c squared, it wouldn't be that much more work. You would just have to have w now equals z over c. And you get a really nice conversion factor between the two. So this is, in some sense, a version of the change of variable formula. But I'm trying not to write down the whole gory version of the change of variable formula, doing it in a very nice situation where we can see clearly how things change. So by contracting and stretching things a little bit, we can convert the ellipse to a circle. We understand how a circle is, and we can use this to record how things change. So in the case we were doing, I think I had a equals 1 and b equals a half. So we did a equals 1, b equals 1/2. So the area for us should have been pi over 2. And that is what we were getting. So this is a way to prove that the numerical results we were getting are reasonable. Okay. Any questions about this? Yes?
What is the Monte Carlo aspect of this?
Right here, the Monte Carlo aspect is choosing the points uniformly in the unit disk or whatever your region and seeing what fraction lie in the set you care about. And the Monte Carlo comes from gambling, and that's where the name comes from. And so the whole point is, if you have good ways to choose points uniformly at random, and you can choose a lot of points, and you can easily tell if you're in the region or not in the region, you can use this to do an outstanding job of estimating the true area, or estimating the area under the curve, or in hyperdimensions, if you have a huge swath in 12-dimensional space. You can then say, well, how many times do I lie inside all the constraints? You can calculate these high-dimensional integrals trivially. It's no longer a difficult problem. It all comes down to, do I satisfy my conditions? Am I in the region? And so you're converting integration, which is hard, to almost set validation. Am I in the set? If yes, count it. If no, don't count it. And then, since I figured most people haven't seen the formula for the area of an ellipse, I thought it would be nice to just use that as an example and then just see how we could actually make a conjecture based on numerics. What you could do, of course, is you could try to see what the functional form should be for the area of an ellipse. So for instance, if I keep A fixed and I double B, what should happen? What should happen to the area? It should double. And so we could actually numerically simulate this by choosing different ellipses and seeing does the area seem to double, and try to actually conjecture what the formula of the ellipse should be based on certain cases. All right, so what I want to do now, Buffon's needle. How many of you have heard of Buffon's needle? You want to say anything about it?
It's basically you're dropping a needle on planks of wood,
Okay.
and you want to know the probability that the needle crosses a slit between planks.
So we're going to assume these slits are d separated, and they go off to infinity. It turns out the answer involves a nice rational multiple of a really nice constant. If you haven't seen this constant before, you are eligible to answer. If you've seen the constant before, please don't speak. Any thoughts what the constant should be? Yes?
Golden ratio.
Golden ratio. So for the golden ratio, you'd want Fibonacci-ness. Don't have Fibonacci-ness, unfortunately. Not a bad guess, but no. I'm sorry? I heard you say two different numbers. Which one?
I said pi.
Okay, you said pi.
I said e.
Yeah, I mean, when in doubt, guess pi, guess e. Those are two of the most fundamental objects. It turns out pi is the one that comes into play. And if you think about it, there's some kind of angular stuff going on that could possibly giving us a pi, or that this is related to, we just talked about the ellipse, which has a pi, and I maybe am focused on pi today, thinking of Thanksgiving coming very, very soon. Okay, pi is going to end up coming to play. What I love about this is the answer for the probability if you drop a piece of a needle of a fixed length L, the probability that it crosses one of these lines is going to be related to something involving L and D, and it's going to be a nice integer multiple or a rational multiple of pi. You can use this to numerically approximate pi by dropping huge numbers of needles on lined paper. Somebody claimed to have done this and calculated pi to 8 digits accuracy. What somebody noticed, however, is that if this person had dropped one more needle, irregardless of how it landed, he would have fallen to about 3 digits accuracy. And it looked suspiciously like this person just happened to choose a really good rational approximation to pi and just pretended that they had done the simulation. The denominator was cherry-picked, and this was just a red flag that something was going on here. But really nice problem. So let's say we have space d between all of them, goes off to infinity, and we have a rod of length L, and I'm going to assume L is less than d. Why might I want to assume L is less than d?
That way it can't cross 2.
That way it can't cross 2. It's only going to be able to cross 1. Okay? So the answer for the probability that you hit is going to be some function of L and D. Can anybody tell me how it should depend on L and D? Any thoughts on how it should depend on L and D?
Should go up with L, but should decrease as D goes up.
Okay. We can do much better than that.
Well, it's also give a square of radius L, or a circle of radius L and a circle of radius D. Or a circle of radius L over 2, so it should be L squared.
I don't want to quite get into the circle, but you can use the circle to do this elementarily without integration. But I want to try to get some sense of how it must depend on L over D. So we just talked about some experiments we could do for the ellipse. What kind of experiment could we do here? So I've got some value of L and D, and then I want a new value of L and D. What would be a really good new value for L and D to take? So maybe my old values were 1 and 2. What would be a good choice for the next one? I'm sorry? 1 and 4 is a possibility, but I think there's something better than 1 and 4. Something in 4. 2 and 4 would be another good one to take. 3 and 6, another good one. 4 and 8. Square root of 2 and 2 root 2. What do you think should be true about the probabilities in all these cases? They should be equal. If I double D and I double L, it's like I've just changed my units. So my answer should actually just be some function of L divided by D. What do you think will happen as L gets really, really small relative to D? Yeah, so I think it's going to be L over D and not D over L. So I think it should be, and I'll conjecture maybe it's going to be some constant times L over D. That would be the nicest possibility if it's like that. We have no idea that it's going to be a constant. It could be L over D squared or L over D cubed or e to the L over D. Any of those are fine. The simplest thing would be if it was constant like that. There are two ways to do this. One way is by brute force integration, and the other way is to consider a very special circle. And if you drop a very special circle, you can guarantee the circle will hit exactly twice. You break the circle up into a lot of different segments. I will send you the write-up of that. I want to do the longer, more painful brute force approach. Okay? So we've got to choose our coordinate systems. We're going to drop a rod. So here's my x-axis. Without loss of generality, and again, when you have so much symmetry, you want to think about how can you use that symmetry to your advantage. I might as well assume the center of my rod lands on the x-axis. Because there's no change as I move up and down vertically. There's no structure, right? So I might as well assume the center lands somewhere on the x-axis. More than just somewhere on the x-axis, if I wanted to, I can assume the center lands somewhere between 0 and d over 2. Because if it lands past over here, I can just take the mirror image and flip it. So you can start doing some simplifications. So let's assume it lands at some point x. And so we'll have 0 less than equal to x less than equal to d over 2. What's the next thing we need to talk about? The angle. What are the possible angles? 0 to pi over 2. All right, so if it starts off at 0, it's like this, to pi over 2 comes up to this. Why couldn't it be like this? I can use symmetry, and over here I could just flip it like that. So again, I'm slightly changing the problem. I'm not doing the original problem that was asked, but I'm doing a problem that has the same answer. So let's do 0 less than equal to theta less than equal to pi over 2. And so now, here's my rod of length L, here's theta. How do I know if I hit? When do we hit? There's got to be a really nice condition. Hit if
Theta is less than 45 degrees.
well, it's going to depend on L. So if this is L, this segment down here is going to be L cosine theta. So we hit if L cosine theta is less than equal to d over 2. Oh, I'm sorry, is less than equal to x? Or greater than equal to x? I think greater than equal to x. If this distance is greater than equal to x, we go all the way back. Yes? L over 2, thank you. So we will hit if L over 2, because each one of these hypotenuses is L over 2, if the cosine of that, theta times L over 2, that's got to be larger than x, so we go all the way back and hit the line. Is it possible for us to hit the line more than once? Do we care about that possibility? The only way is if we drop the line perfectly, aligning with the line. That happens with probability 0, so we just ignore that. So now this is going to give us the probability of a hit. So the probability of a hit, we integrate x goes from 0 to d halves. We integrate theta goes from, so now I've got to figure out what the range is for theta. Can somebody give me a value of theta where we definitely hit? 0. And then what's the largest value of theta we can go up to? Arc cosine of 2x divided by L of 1 d theta dx. Anybody want to do that integral? Okay, what else could we do instead of writing the integral this way? I mean, if we do this integral, the integral of d theta is just theta, so we get arc cosine of 2xl, then we have to integrate arc cosine. Is there another way we could do this problem? I'm sorry? Yeah, switch x and theta. We don't know that much in linear and multivariable calculus. We can change variables and we can switch orders of integration. So let's do the theta integral first. Theta goes from 0, and how high can theta go up to? Pi over 2. And then for a given value of theta, what's the range for x? Well, clearly if x equals 0, it's going to work. And then how high can x go up to? Oh, this is much nicer. L over 2 cosine theta. 1 dx d theta. I can integrate cosine. Right? This is the power of switching orders of integration. Frequently, one is going to be significantly easier than the other. And so if we switch, we now get the integral theta goes from 0 to pi halves. The x integral is just going to give us L over 2 cosine theta d theta. All right, so we get L over 2. Now we have to integrate theta goes from 0 to pi halves cosine theta d theta. What function integrates to what function has derivative cosine? Sine. So this is L halves sine of pi halves minus the sine of 0. And we get L halves. So we've only made one mistake. I'm sorry? We don't have d anywhere, and we don't have any pi, and I claimed that there was supposed to be a pi. So where's the mistake?
Don't we need to normalize by the...
We need to normalize, right? What's the region of space we're looking at? What's this region? It's d halves times pi halves. So the region of space is d pi over 4. So we need to integrate not over this, but we have to divide by pi d over 4. And we need to put in a 4 over pi d, 4 over pi d, 4 over pi d, and now we get 2L over pi d, or 2 over pi times L over d. And there's the answer, a nice rational multiple of pi. Great way to end right before Thanksgiving. Okay, I'll send a much better way to do this without integrating by just throwing circles. But this shows you, the conditional probability. We've got to make sure we normalize. This shows looking at the right way to represent the integral. Sometimes one way is better than another. There's a lot of really good ideas here.